Guys, muscle physiology, one of my favourites, should be one of your favourites. Great intro here. I've got two highly adapted athletes. We've got one on the left, Dorian Yates, 6 times Mr. Olympia, happens to be British. The lady on the right, Paula Radcliffe, Olympic champion, marathon runner, also happens to be British. Not the point though here. Point being is both have highly adapted respective muscle fibres, but with very different outcomes, as you can see. But both have particularly chosen a particular fibre to adapt to its full potential. And as you can see, there's very different outcomes here, but both could be considered elite in their respective fibre choice. Alright guys, we've got 3 types of skeletal muscle contraction here. We've just got a security breach here just coming up. Right, 3 types of muscle tissue found within the body. Smooth muscle, cardiac, skeletal. Smooth, under involuntary control. We find that within the digestive tracts, continual contraction to propel food. Cardiac muscle, striated, not smooth, special fibres which can distribute a signal throughout the heart. That's where that stops. Skeletal, it attaches itself over joints. Okay, it's under both the control of the voluntary system. We can choose to contract this, but also involuntary, such as when we shiver, reflex arc is in a patellar reflex or a hot plate, so it's under both voluntary and involuntary. But obviously, we are thinking of it as a voluntary controlled muscle. Right, this is important, you have to get this one across well. A muscle, this is a generic muscle, attaches itself to a bone via a tendon. The bone itself has a nice periosteum, a vascular covering, making this particular attachment ideal. Okay. Now that tendon blends over to form a fascial covering. A fascial covering. This may be the first time a student's ever heard the word fascia. Fascia is a opaque connective tissue found over a muscle, designed to keep it both in groups and to prevent the friction of muscles rubbing against each other. So, that tendon will blend over a muscle. The tendon itself was made up of elastin and collagen, okay, making it quite stretchy and tolerant to forces. It will indeed, such as within muscle, respond to loading by increasing its collagen alignment, making it stronger and more robust and able to tolerate higher loads and higher intensities. So important to understand that this will adapt as well as the muscle itself. So let's get on to the muscle. So the tendon will blend over to form a fascial covering. Now, that fascial covering is called the epimysium, okay, which, as you can see there, if we chop and sagittally dissect this muscle and pull out what appears to be a bunch of spaghetti, okay, that bunch of spaghetti or that bunch of muscle fibers is called a fascicle, okay, a fascicle, a fasciculus, or indeed plural, fasciculi. Okay, now we've got a bunch of spaghetti, which in itself has its own fascial covering. We call that fascial covering the perimysium. The perimeter of the fascicles encompassed by the perimysium. Now let's pull out one strand or one muscle fibre. Now that muscle fibre, we're on a scale of when you tear open a Colonel Saunders KFC chicken breast and you see the stringy type fibres, that is the scale on which we're looking at. They are muscle fibres. Okay. Now we've got a bunch of muscle fibres called a fascicle. If we pull out one muscle fibre, that muscle fibre has its own fascial covering, in which we call the endomysium. Now we pull out one strand of spaghetti here. We dissect that. What we can pull out from that are many myofibrils. Many myofibrils, which is the contractile unit of the muscle. If we dissect a myofibril, we can pull out thousands upon thousands of filaments. Okay, and these are the actin and myosin filaments. So overall, what we have are lots of these within those, lots of these within the fibre, lots of fibres within the fascicles, and lots of fasciculi within a muscle, making for an entire living contractile tissue. Okay, these are the 2 filaments in question. The thicker filaments, M for muscle or large, myosin. The thin filament, the blue one, actin. These golf head structures are called cross bridges. Okay, myosin cross bridges. Now they will have a particular sequence of events that will create this muscle to contract. We have the preparation, okay, the binding of these cross bridges to the actin, the power stroke, and the detachment. Okay, think of it as either two sets of rowers, rowers, and these are oars, and the blue actin is the water, and they are pulling themselves along all together at the same time. This is showing us one sarcomere. Now this is relaxed and this is contracted. Okay. Here we are. This is just a representation of it as a photo or under an electrical microscope, and this is the actual illustration. Not much to know here. It's just a description that these H zones will overlap, and there's not much requirement for here, but the thick filaments being the myosin and the thin filaments being the actin. Right, this is just an overview. Muscle broken down into fascicles, pulling out into a single muscle fibre. If we expand on that, we've got many myofibrils that contract our unit within a muscle fibre. Many actin and myosin filaments within a myofibril. Now, this is important to note. What is it about muscle tissue that makes it so unique? It has the ability to shorten beyond its resting length. A bone or this pen cannot get any shorter than its resting length. It can contract and go within itself. It will respond to an electrical stimuli, so it has properties of excitability. Okay, adipose tissue and bone doesn't have the same response. Okay, so it has the property of excitability. It will do something when an electrical impulse is generated to it. It can go beyond its resting length. It can go beyond its resting length, and we call that extensibility. Once it goes beyond its resting length, it will go back to its previous resting length, and that is the elasticity property that it possesses. Okay, functions like anything, everything has a function. The skeletal muscle attaches itself over joints. It crosses over joints, or when it attaches over joints and contracts, creates movement. You might want to just get the skeleton out here and just show the students that simply put, the skeleton is a series of levers, if you like. Now, if you attach a contractile tissue that can be contracted upon command via the central nervous system, attach that over joints, allow an electrical impulse, those two attachments will cause movement. Okay, so it allows movement of the skeleton. It maintains body position, okay, and posture. So it maintains body position and posture by allowing us to walk upright against this perpetual force of gravity, which is pushing us against the earth around about 9.3, 9.8 meters per second. It supports soft tissues. Okay, so if we just merge over to the left here, if you're having a look at this anatomical muscle chart, having a muscular abdominal wall, there are no ribs here. There are no ribs here, so it allows a framework or a scaffolding for the internal organs to sit in. Okay, it allows a framework or a scaffolding in which the organs can sit in, so it supports soft tissues. Just moving back to the slides here, we can see that it also guards entrances and exits. Now I make a joke out of this one, and that if I had no pelvic floor and I jumped up and down, my entire insides would flush out onto the floor and I would have to embarrassingly stuff them back in. So having a pelvic floor guards entrances and exits. It maintains body temperature. When the thermoregulation, the body thinks it's a bit cold, it will generate heat by promoting muscle contraction. That is shivering. Thermoregulation, a homeostatic response. Right, this is the sliding filament theory. 4 stages. The preparation phase, you've got a cocked cross bridge that binds itself to the binding sites, the calcium binding sites of the actin filament, pulls itself along and detaches. Okay, it's all explained here in a nice little illustration, or I should say a cartoon. So you can see the preparation phase, binding, power stroke, detachment, showing us here the sliding of the actin and myosin filament. All the other stuff is not really needs to know. It's got splitting of ATP and some calcium, but not necessarily. I've left the key out especially, but this gets into view exactly what's going on. Now these 4 stages, one cross-bridge cycle is thought to shorten a muscle by about 1%. So to create a full flexion of the elbow and shoulder, you'll get 100 of these cycles occurring. So it shows you the rapidity, okay, and the intricacy we're looking at. We're looking at a semi-molecular level here, okay, a semi-molecular level. Now, in regards to muscle, it's important for them to understand what an origin is and an insertion, okay, which is, an origin is where the muscle begins, and the insertion is where the muscle will insert. Now the insertion will always move towards the origin. The insertion will always move towards the origin. And the origin is the fixed component. There are exceptions, however. The torso, the abdominal, the obliques muscles, they can have reverse origins and insertions. I.e., I can bring my ribs towards my pubis, or I can bring my pubis towards my ribs and allow the top end to fixate. So they are the exceptions. Rectus abdominis can have a reverse origin and an insertion. Both can move, but other muscles have a standard arrangement. Right, muscle contractions here, very, very, very important here. Concentric is when a muscle shortens under tension. Okay, shortens under tension. It is the weakest in terms of force production. Eccentric is when the muscle lengthens under tension. It is the phase, the more productive phase, because we get more mechanical stress, more myofibrillar damage, and therefore more adaptations such as hypertrophy and strength occurs in this phase. This will work generally against gravity. Hence we are 15% stronger here to help cope with the extra force we're working against. Okay, because this is our decelerative muscle contraction. Isometric, iso meaning same, metric meaning length. No change in net length, but there is a contraction. Okay, a static contraction here. Nicely put here. Guy's gone from horizontal to vertical and then back down. On the way up, there must be the tissue shortening to get him upwards, and on the way down, he didn't drop himself down or wasn't pushed. He decelerated himself down. So his muscles gradually lengthened under tension. Okay, some terminology here, really, really important. The prime mover is the major muscle contracting to cause that movement, also called agonist. It will be the same on the concentric or eccentric. The antagonist is the opposing muscle, which must relax to allow the agonist to perform its role. Okay, examples of muscles with an antagonistic relationship: biceps and triceps, quadriceps and hamstrings, rectus abdominals and rectus spinae, just to name a few. Now, an assister or a synergist is the smaller muscle, not the dominant contributor, assisting the agonist to perform its role. Okay, the stabilizer, as we know, is a stabilizer muscle which will work isometrically to stabilize a segment or joint to allow that movement to occur. Okay, this is important, guys. Fibre types. We've got Paula Radcliffe, an elite marathon runner here, endurance athlete on the right, and she might have a highly developed slow twitch type 1 fibres. Now these type 1 fibres are slow to fatigue, okay, and that they go on for ages, but they don't produce high amounts of force. The reason they do not produce high amounts of force is because they have limited cross bridges. Okay, they have limited cross bridges. Now, what determines the force production of a fibre are its number of cross bridges, golf clubs, cross bridge heads, myosin heads. The greater the number of myosin heads, the more force can be produced. These muscles have low number of myosin heads, high number of mitochondria, because they require oxygen to metabolize foods to create ATP. Now, what happens here with these fibers, Paula Radcliffe has trained these fibers to be able to aerobically produce ATP, which means she has trained them so that her mitochondrial, aka cooking pot, number and density will go up along with size. Okay, so if you've got larger cooking pots with more of them, you are able to create or cook up more ATP aerobically. Now they are red in colour, hence if you notice the difference in colour between thigh meat in poultry and breast meat. You'll see that the thigh meat or leg meat is slightly pinky in colour. The reason being the chicken was walking on its legs throughout its life. When it was killed, there was more blood in that area. Chicken pecks, on the other hand, chicken pecks, as we can see, are white in colour, and that's thought as white meat. The reason being, chickens have an anaerobic flutter, they don't fly anymore. Those muscles now have adapted to become fast twitch in nature, hence the white colour, less blood, less oxygen. What we've got here are two bodybuilders, Tom Platt on the right, nice to know, Dorian Yates on the left. Neither will be in the test or the assessment, but just quite a fun thing to show how these fibres adapt. Now these are your major force producing fibres. But the reason why they are their major force producing fibres is because they have a very high number of cross bridges on them, making them a high affinity to create force. They are nicknamed your fast twitch fibres. They fatigue quite quickly, but they contract very quickly. Low in O2 and mitochondria, and therefore all white in colour. Okay, now types of adaptation. I put this on here, guys, just to give students an idea that there's different ways that the body can adapt. Morphological adaptation, it could be thought of a change in morphology. It might be an increase in muscle fibre diameter, bone density, or bone remodelling. Okay, we can see that the previous chaps before us adapted very well morphologically. Okay, they therefore chose the fibre which will adapt morphologically, and that is obviously the type 2X fibre. Paula Radcliffe, although the entire process works under the physiological system, of course, but to make it easy for students to understand, Paula Radcliffe has increased her number and size of her mitochondria. So she's manipulated that this particular muscle cell or muscle fibre will get better at oxidatively producing ATP, and therefore will increase its size of cooking pots and number of them. And you can also have a neurological increase or an adaptation, which is considered an increase in pathways from the brain to the muscle, so an increase in neuromuscular pathways. Nice to point out with this one, in the absence of hypertrophy in the untrained, if you think of the students, put it to them of asking them, when you first started lifting resistance training, or started lifting weights in your resistance training, they would have seen a relatively rapid increase in strength, but in the absence of hypertrophy. The reason for this is not one of thickening of fibres, was because they were able to recruit more of their muscles because they had an increase in neural pathways. Okay? Now there is a correlation between all three, and they can assist in one or the other, but it's important to understand that hypertrophy is one adaptation and strength is another, but both are mutually exclusive. Having an increase in neuromuscular adaptations will allow you to recruit more of the muscle. Having thicker muscle fibres will allow those fibres to tolerate more loads. So an Olympic lifter looks nothing like a bodybuilder, but can create much more force than a bodybuilder. A bodybuilder looks much stronger than an Olympic lifter, but it is nowhere near as strong because he or she has gone purely for the morphological adaptation. Okay. Now then, as you said, they may be marginally higher from the untrained of red slow twitch in fibres and thighs, or slightly higher in areas that require higher recruitment, such as chest muscles or chicken pecs, as we say. Now, just moving over to the board briefly, I'd just like to point out, after I move the bones out of the way. Okay, so we've got our type 1 and our type 2A and our type 2X. Okay, these guys use the aerobic system. Okay, they are aerobic. Our type 2A, which is not in the literature, but is important to understand, these are our intermittent fibres. Okay, and our type 2X used to be called type 2B. Type 2B fibres are only found in animals. In humans they are called type 2X. These are our anaerobic Now, these guys have a high number of mitochondria, okay? Type 2A fibers can show characteristics of either way depending on the stimulus they're given. So we call these muscle fibers fence sitters. They're fence sitters. They're neither fast nor slow, but can show characteristics of either way depending on what stimulus you've got. But you cannot change a type 1 or a type 2. They are set in stone. So if you are born with a high amount of type 2X fibers, then the person next to you will probably favour hypertrophy, power type events. If you're born naturally with a higher amount of aerobic fibers, you are naturally favour endurance events. You can change your type 2A depending on what you give it. Okay, now just to relay this to resistance training, these anaerobic fibers will use the ATP-CP system. Okay, which we know goes for 1 to 15 seconds. Now, if they use the lactic acid, which they can also start to use, we're looking at around about 1 to 15 plus 1 to 3 minutes of intense work. Now, again, looking at that hypertrophy picture of these chaps here, just having a look at that and coming back to the board, what we find, if we know that a working set of optimal hypertrophy is around about 8 repetitions on average, 8 to 12 we'll say, if we know that each rep takes about 5 seconds in length, if you times that 8 to 12 by 5 seconds, you get around about 60 seconds of muscular contractions. Now that all links in nicely to the energy systems because that is working nicely, the ATP-CP lactic acid system. There's our 60 seconds, there's our type 2X. These guys will respond by increasing their fiber diameter. Okay? These are our body pump, intermittent, and these are our long distance events. Okay, so this is our 15-minute plus dominant duration energy system. Okay, and we've got lots of cooking pots, lots of capillaries. Okay, these can show either way, characteristics of either way. Okay, what I've explained here is time under tension, in that really reps are a way of counting time. Okay, instead of counting 60 seconds, let's count reps, knowing that each rep takes around about 5 seconds, 60 seconds. Okay, moving back over to the board here. What we've got are muscle fibre arrangement, guys. Muscle fibre arrangement, longitudinal end-to-end fibres running parallel to each other. They've given us the example of the sartorius muscle, aka talar, that's what it means. We've got the next one, the unipennant, one side of a angled fibre. So you've got half a feather, a tendon on one side with fibres coming off at an angle. They've given us the tibularis anterior here as an example. A bipennate muscle, very powerful central tendon with fibres running off each side. We've got rectus femoris here as an example, which crosses both the hip and the knee. It needs to have that arrangement because it needs to be able to create maximal forces because it's spanning over 2 joints. Our multipennate muscle, we've got here the deltoid, which shows us there's fibres in many directions. In this case, we've got fibres running backwards, the posterior delt. Vertically, the medial delt, and then anteriorly at an angle, that is the anterior delt. That will facilitate the joint of the rotary joint, that is the glenohumeral joint. Full 360 movement, many types of motion, having a muscle that can move in many directions will facilitate this type of joint. Having a longitudinal muscle on a ball and socket joint wouldn't allow us to take full advantage of those characteristics. We've got the radial muscle here, very broad origin, very broad insertion, all converged to one common insertion. This is pec major they've given us. Okay, fan-shaped muscle, radial muscle, fibres coming off nearly vertically, fibres nearly transverse, and fibres nearly vertically again coming downwards, with a common insertion towards the bicipital groove of the humerus. Okay, so what we've got here is a fibre that can work and create a little bit of flexion. Okay, horizontal flexion, okay, and moving from down to vertical flexion again. Important to understand with pec major, one nerve supply. There's no such thing as upper pectorals, middle pectorals, or lower pectorals, but there are fibers which run upwards, middle, and down, and we can influence the amount of activity those regions get. And from a perspective of hypertrophy, it might be advantageous to work those different regions. That's where the incline, flat, and decline bench presses flies come from. And that's muscle physiology.